so for in the principles of experimental design, there are three important things. One is you want to control for lurking variables that might affect your response. You want to use comparative design and ensure that only systemic differences between the groups is the treatment that you're administering. That was what we talked about with lurking and confounding. You want to randomly assign things. You want to have an impersonal chance to assign experimental units. That's why we use this random table all the time. And that way we get roughly equivalent groups. So like in the last one, we had 29 people, so there was 15 and 14. It's not always exactly even, but we try as best we can. And number three is replication. You want to have enough experimental units so that any differences in the effects can be distinguished from chance differences. So for example, does caffeine affect your pulse rate? Many students regularly consume caffeinated products to help them stay alert. It seems plausible that taking caffeine might increase your pulse rate then. One way to investigate is to have volunteers measure their pulse rate, drink some cola with caffeine, measure pulses again in 10 minutes, and calculate the increase in your pulse rate. How do we use all three principles? And let's look at one at a time, I guess. Number one, when you're controlling, you would want to make sure that you have a control group with non-caffeine cola. All subjects that are not in this group should get the same amount of cola the cola should be served at the same temp. You don't want it to be ice cold, you want to be warm.
Yep.
It should be the same cola so that it looks and tastes the same. The subjects should drink it, if you can really control for this, at the same rate. Some people like to slam their pop, some people like to sip their pop, so have everybody do the same thing. Pulse rates should be measured after the same amount of time. What else? Yeah, maybe the same amount of activity. So the activity level should be the same. And basically what you're trying to do here is you're trying to reduce the number of lurking or confounding variables. That's the whole purpose of this control. All right, next, let's talk about number two, the randomization. Yeah, there's a lot of writing. I'm sorry.
Where?
Randomly assign our subjects, because they're people, to one of the two treatments. And I'm running out of room, but you probably should mention what they are in parentheses. Caffeinated, non-caffeinated soda. So this might speak here, Will, to what you were talking about before. There were some things we didn't mention. So when you randomly assign these people, this will hopefully eliminate the lurking variables possibly weight of subject, and Will, the other one you mentioned was caffeine tolerance?
Yeah.
And caffeine tolerance, among others. The last thing that we want to talk about was replication. So here's where we want to use as many subjects as possible to reduce chance variation. This phrase is very important. This chance variation thing. They talk about it a lot. And thereby see the effects of caffeine on pulse rate. Was there anything else we were talking about? Pulse rate and... No, not really. Okay, so in this last slide for today, some other experimental terms that you should know. A placebo is a fake treatment. So sometimes, they talk about taking aspirin to get rid of a headache. But maybe it's not just the aspirin. Maybe you drink lots of water, you lie down in a dark room, and you're good to go. So it's kind of like being a control group treatment, the placebo. The placebo effect is when a patient gets better using a placebo because they believe that they actually received the treatment. A double-blind study is when neither the subjects nor the people who are interacting with them, which means pretty much the experimenters, measure the response variable and they don't know which treatment the subject received. Double-blind. Just to see what the actual results were and say, oh, do I see something then? And then later on they can always go back and look at that information. So when they actually are doing the treatments, they don't know. But then they can go back and reference the table and then pick out who was in which group. So in the end they know, but not when it's happening. And statistically significant. An observed value that's so large that it would rarely occur by chance. For some reason in statistics, we use the percentage 5%. Example. Researchers are examining the effect of ultrasound on birth weight. Pregnant women participating in the study were randomly assigned to one of two groups. The first group received an ultrasound. The second group did not. When the babies were born, their birth weights were recorded. The women who received the ultrasounds had heavier babies. Did the experimental design take the placebo effect into account? All right, so no is the basic answer. Why is this important? Maybe the women getting the ultrasound did something different during pregnancy knowing they would be recorded. Like, for example, what if they ate healthier?
Well, in that case, it would be though.
No. The people, but I'm going to use part of that. The people weighing the babies did not know if the women got an ultrasound, but the mothers knew. So one group did not, the weighers did not, but the moms knew. So it's not a double blind, it's a single blind. Yeah. And that would be talking about all the single ladies. All right, I want you to try part C. Based on the answers, improve the design. What would you do differently so that it'd be better?
You're still recording.
Oh, all right.
You didn't get the.
I would say that all the doctors use the ultrasound machine but only turn it on for half of the mothers. In addition to that, we also talked about the doctors should turn the screen away from the moms, and maybe, if I remember right, there's sound, and shut up the sound.
So then it's just all